In the last video, we looked at a function and tried to draw its derivative. Now in this video, we're going to look at a function and try to draw its antiderivative. Antiderivative, which sounds like a very fancy word, but it's just saying the antiderivative of a function is a function whose derivative is that function. So for example, if we have f of x, and let's say that the antiderivative of f of x is capital F of x, and tends to be the notation when you're talking about an antiderivative. This literally just means that the derivative of capital F of x, which is equal to, you could say capital F prime of x, is equal to f of x. So what we're going to try to do here is we have our f of x, and we're going to try to think about what's a possible function that this could be the derivative of. And you're going to study this in much more depth when you start looking at integral calculus. But there's actually many possible functions that this could be the derivative of. And our goal in this video is just to draw a reasonable possibility. So let's think about it a little bit. So let's, over here on the top, draw y is equal to capital F of x. So what we're going to try to draw is a function where its derivative could look like this. So what we're essentially doing is when we go from what we draw up here to this, we're taking the derivative. So let's think about what this function could look like. So when we look at its derivative, it says over this interval, over this first interval right over here, let me do this in purple. It says over this interval from x is equal to 0 all the way to whatever value of x, this right over here, it says that the slope is a constant positive 1. So let me draw a line with a slope of a constant positive 1. And I could shift that line up and down. Once again, there's many possible antiderivatives. I will just pick a reasonable one. So I could have a line that looks something like this. I could have a line that looks something like this. I want to draw a slope of positive 1 as best as I can. So let's say it looks something like this. And I could make the function defined here or undefined here. The derivative is undefined at this point. I could make the function defined or undefined as I see fit. This will probably be a point of discontinuity on the original function. It doesn't have to be, but I'm just trying to draw a possible function. So let's just say it actually is defined at that point right over there. But since this is going to be discontinuous, the derivative is going to be undefined at that point. So that's that first interval. Now let's look at the second interval. The second interval from where that first interval ended all the way to right over here. The derivative is a constant negative 2. So that means over here I'm going to have a line of constant negative slope or constant negative 2 slope. So it's going to be twice as steep as this one right over here. So I actually could just draw it. I could make it a continuous function. I could just make a negative 2 slope just like this. And it looks like this interval is about half as long as this interval, so it maybe gets to the exact same point. So it could look something, let me draw it a little bit neater. It could look something like this. Could look something like this. This slope right over here is equal to 1. We see that right over there in the derivative. And then the slope right over here is equal to negative 2. We see that in the derivative. Now things get interesting. Once again, I could have shifted this blue line up and down. I did not have to construct a continuous function like this, but I'm doing it just for fun. There's many possible antiderivatives of this function. Now what's going on over the next interval? What is going on over this next interval? And I'll do it in orange. The slope starts off at a very high value, or it starts off at positive 2. Then it keeps decreasing, and it gets to 0 right over here. The slope gets to 0 right over there. And then it starts becoming more and more and more and more negative. So I'll just try to make this a continuous function just for fun. Once again, it does not have to be. So over here, the slope is very positive. It's a positive 2. So our slope is going to be like, this is negative 2, so it's going to be a positive 2. And then it gets more and more and more negative up to this point, or it becomes less and less and less positive, I should say. Even here, the slope is positive. And it gets to 0 right over there. So maybe it gets to 0 It gets to 0, maybe right over here. And so what we could have some type of a parabola, so a downward-facing parabola. So notice the slope is a very positive value. It's a positive 2 right over here. Then it becomes less and less and less and less positive all the way to 0 right over there. And then the slope starts turning negative. Then the slope starts turning negative. And so our function could look something like that over the interval. Let me draw it a little bit. Let me draw it a little bit neater. This is symmetric. However positive our slope was here, it's equally negative here, so our curve should probably be symmetric as well. So let me draw it. Let me draw it like this. So over that interval, it could look like that. And then finally, over this last interval, or as I guess we could say it keeps going, our slope is 0. Our slope is 0 right over here. And once again, I don't have to draw a continuous function. But when the slope is 0, that just means that I have a line with slope 0. I have a horizontal line. And I could draw that horizontal line up here, in which case I'd have to say it's discontinuous. Or I could draw that horizontal line right over here and try to make my antiderivative a continuous function. So once again, I could have shifted any of these segments up or down and gotten the exact same derivative, but then I would not have gotten a continuous function like this. But we have been able to construct a possible antiderivative for f of x. And just as a reminder, that's just saying this f of x is the antiderivative is a function that f of x could be the derivative of.